All right, welcome to the 140 session. Our first speaker is LVH. He's going to be talking about distributed systems. Thank you.
Hi, everyone. Welcome to your scheduled post-lunch lull. Hope you all had a good lunch. I'm going to be talking about an introduction to distributed systems. It is fairly introductory, so if you have some experience, I will not be offended if you walk out. The slides are already online. I'll be showing the link again at the end. So brief introduction. I'm LVH. Hi. We're at PyCon. I'm sure you've gathered. PyCon is a very special time of the year for me. There's a lot of friends that I only get to see about once a year, and it's at PyCon. This year, I have a couple of staff positions and 2 talk slots. I'm not trying to brag. That's more of an apology in advance. I've been running on what I can only describe as a very serious sleep deficit. So with a little bit of luck, I'm going to be coherent during these 45 minutes. There's only one way to find out. I work at Rackspace. It's a cool place to work. We're a sponsor. You should come look at the booth. And at Rackspace, most of my work so far has been on a project called Autoscale, which internally is codenamed Otter. Just gives me an excuse to put cute animal pictures in my slides. Now, I wouldn't normally mention that, except that Autoscale is very interesting to distributed systems, because Autoscale itself is a distributed system, but it also manages distributed systems. And all of those are running on top of distributed systems. And all of the systems that it orchestrates are distributed systems. And it's doing that at a fairly reasonable scale. So we see some interesting things. The goals for today is basically just enough distributed systems to whet your appetite and to shoot yourself in the foot. These are not opposing goals. These are basically exactly the same thing. Now, my goals today are not to be exhaustive and not to be pedantically correct. I'm not saying that mathematical correctness is somehow not important or anything. I'm just saying I don't have enough time to spend on strict mathematical correctness. So it is just to give you an idea of what there is and where to look and convince you that distributed systems are tricky. Which is somewhat paradoxically, that means that the worse a job I do as a presenter, you think it's more complicated, and therefore I've succeeded and I've actually done better. So, cool. Anyway, so distributed systems, what's up with that? Leslie Lamport has a quote that says, a system is distributed when a machine that I have never heard of can somehow cause my program to fail. Now that actually brings us to a paradox, because I've talked to a lot of people that operate distributed systems for a variety of reasons, and when people tell me why they do so, the answer is almost always availability, right? It's reliability, it's availability. Why? Usually it's a distributed database, and the reason they use that instead of something that's not distributed is because it fails less often, allegedly. But when you listen to experts in the field, like the only thing that they always mention is super special about distributed systems, and what makes them so hard is failure. So that's an interesting paradox, and hopefully we'll be able to elaborate on that a little bit more during this talk. Now, distributed systems are really just systems that abide by 2 fundamental constraints. First of all, information travels at the speed of light. No faster, usually slower. And secondly, components fail. So 2 very simple things, and basically anything that has to deal with this is probably distributed. Sun produced a list of fallacies. So these are things that many junior engineers, when they start doing distributed systems, that they believe, but end up invariably being false. We're going to deal mostly with the top couple of these in this talk. So there's the network is reliable. It's not. It fails. Latency isn't 0. It takes a while to get packets from one side of a data center to the other. Bandwidth isn't infinite. The network is generally hella insecure. Topology changes all of the time. There are plenty of administrators, and they have different bosses. Transport cost is pretty high most of the time, and the network is anything but homogeneous. There's lots of different kinds of clients. So what's an example of a distributed system? Now, somewhat facetiously, I could say, well, basically everything, which includes your laptop. Because, hey, the speed of light isn't infinite. When your CPU has to go get something from RAM, it's like 2 whole inches away, or maybe 1 whole inch. Like, that's nanoseconds. It's forever. So you could actually see distributed systems effects even on modern desktop machines, modern laptop machines, modern servers. But typically, when someone talks about it, what they mean is any system with more than 1 machine, and they're connected via a network. The fundamental difference between these is that networks fail far more often. Think about it like downtime for a network per year is like measured in, say, hours. But it would not be acceptable for your RAM to not work 1 hour out of the year. So I'm going to talk about some bad news, which is mostly theory and its consequences. And the most famous theorem is probably the CAP theorem. This is something that everybody talks about all the time when talking about distributed systems. And the CAP theorem basically says that you can have any two. You can either be consistent, you can be available, or you can be partition tolerant. You can pick any two of those, but not all three. So what does that even mean, right? Because I just said a bunch of words, but whatever, man. So consistency means linearizability. And I realize I just used a word that you don't understand yet and explained it in terms of a word that you don't understand yet. You can probably think of it as what you expect Python to do on your local machine, like when you assign stuff to names. That's like more or less linearizability. For now, that's good enough. Availability means that all active nodes will answer any query, and partition tolerance is basically resistance to failure. So when I say pick any two, you have this neat little Venn diagram that means that you probably want to be in the intersections of any two, except you can't be in the middle because that would mean all three. Now it turns out that you can't actually sacrifice partition tolerance. Why? Because partition tolerance is failure tolerance. Networks and nodes fail all of the time. Latency happens and is generally more or less indistinguishable from actual failures. The other thing is that systems fail and systems fail partially. So the odds that nothing goes wrong is actually smaller than the complement of the odds that every single individual machine works well. Because you have to keep in mind, a lot of failures are cascading. So if some of your nodes blow up, then you increase the load on the other nodes, and therefore stuff happens. If you have a power spike and it fries a couple of PSUs, it's probably going to fry more than one power supply, et cetera, et cetera. So when somebody says that they pick CA out of the CAP theorem, therefore not partition tolerance, what they're actually saying is it doesn't actually work. So that thing is red. Red means don't pick it. For those of you with color vision issues, I'm sorry. It's the bottom one that you can't have. So an example of a CP system would be Zookeeper, so that because it's CP, you get consistent ops, you get things that look like you're doing it locally, except sometimes they have to fail, because if you pick CP, you're necessarily picking not A. You're not picking availability. The opposite is, for example, Cassandra. You get inconsistent ops. Sometimes stuff doesn't really work as you would expect it locally, but they have a much, much higher chance of succeeding. So informally, let's take a look at a 5-node cluster. So you got 5 nodes, they're connected, cool. So what happens when stuff fails? I still want to read and write, right? I mean, if anything fails and then everything stops working, that's not very useful. So a very common idea is majority quorum. So the idea is, look, if I have a majority, then we can still keep going, right? That kind of makes sense. So if you have a couple of failures, so all the network connections leaving from D and E have failed, then you can still keep going because, hey, A, B, and C, they've got quorum. I said earlier that network connections are pretty much indistinguishable from node failures. You'll notice that if I drew it differently. Now the nodes have failed and the network connections are just gray, but this looks exactly the same from the point of view of the quorum group, which is A, B, and C. And if there's too many failures, then you can't get quorum, right? So it falls over. It's cool. You can still do consistent reads and writes, except you can't. So this is an example of a failure that would break this. And that actually happens reasonably often. I'm not saying this specific thing, but failures where simple models like, oh, quorum consensus, that's a form of consensus, right? So in this case, A can participate in both groups, and therefore D and E might be convinced, oh, yeah, no, we can still do writes. We've got quorum consensus. It's cool. So this is not far-fetched because real failures are typically partial and quite complex. It makes sense for stuff to be partial, right? If you have 100 machines, they're not all going to fail at the same time. You're going to get one or a couple or a handful that don't work. So back to reality. So cap C is linearizability. I said that's like a local Python. And caps A is any operation on any node will succeed unless that node itself has failed. Now those are extremely strong guarantees. So when it gets really interesting is you can't sacrifice partition tolerance, right? So that's the bar on top. No matter where you are, you always get partition tolerance. You have to. However, you can have gradations between availability and consistency. And you can make trade-offs. Like sometimes you don't need pure availability. You don't need pure consistency. There's a lot of really interesting stuff in the middle. You get to trade availability for consistency. Another way of saying that very often is performance versus ease of reasoning about the system. Or like, computer time versus developer time. Usually available systems are more scalable, like a lot of these databases, like for example Cassandra, if you need more write throughput, throw some more machines at it, it'll probably work. On the other hand, like you give up transactionality. So if your business logic requires that you actually do some stuff atomically and transactionally, well, you can't actually do that. So there is no universally correct choice. It's about what your application needs. An example of a creative sacrifice is in etc. So etc is a thing that people use to put some configuration files in. Normally, it should be consistency all the way. That was the idea. This was actually originally found as a bug. I think this is my favorite example of something where people were actually arguing if it's a bug or a feature. etc gives you the option of doing inconsistent reads. And what that means is, like, you're not actually guaranteed that if you do the same read multiple times, you're going to get the same thing. Maybe you're going to get some stale data. But the good news is it still works even under partial failures when doing a consistent, expensive read might have failed. And you don't always need strict consistency, right? Sometimes it's totally OK that you get a value from 5 minutes ago. Now, the way that this stuff works is formally called consistency models. And we're going to talk about those for a bit. So we talked about really simple ones. This is the way Python works, right? If I have a process and a register, when I say register, just think like a Python name. I'm doing like x is some object. So if I write x, and then I do a read, and I always get x back. And if I then write y, and I do another read, then I always get y back, right? That's how it works. It's easy. It's how you expect it to work. And even if you have multiple threads or coroutines, so you have multiple processes writing to the same register, you always get the most recently written value. Right? That's how we expect stuff to work. How else could it? Now, the problem is that we are a spoiled bunch because this is actually an extremely strong model, which in a distributed system is extremely difficult to realize. First of all, information travels at the speed of light. So those neat little straight arrows that I drew, they're actually a little slanted because it takes a while. Right? So you write x, and then you've written x, and you do a read, and then you read x again, but it takes a while. And when stuff is slow, that means it can overlap. So for example, here, process B issues a read. Now, process B is in a data center far, far away. Process A is in the same data center. And process A issues a write, hits the register, it's written, and by the time that read that process B issued comes back, like it's already read that new value. So it's entirely possible that you read something that wasn't written yet by the time you started reading. It's a little weird, but we can work with that. Let's say that you have multiple nodes that store a register, and you have one process, and it's writing something to a node, and then it issues a read, but oh, it hits the other node for some reason, right? Either it's randomized, or maybe that node is unavailable for whatever reason. It is entirely possible that you don't read the same value that you just written again, because it hasn't been replicated to all of the nodes. So you can totally read old data. That's a little weirder. Maybe we can still work with that. A lot of writes can get reordered. So let's say that you have two processes and two nodes, and you're doing an append on one side and an append on the other side. And when they get replicated, it's entirely possible, if we just pretend that this is Python and you do list.append, then if you just shove appends around, then anytime that you read from node A, you're going to see xy. Anytime you read from node B, you're going to see yx. That's a little weirder. Now, it turns out all sorts of stuff can happen. This is just a couple of really simple examples that were easy to draw in my schematic tool. But once you have multiple registers, more semantics, more nodes, more node failures, et cetera, then you can absolutely get into a bunch of trouble. So we need a way to reason about the system, right? We need to figure out what can and cannot happen. It's very clear that it's basically impossible to write software if the contract that you get with that software is, well, I'm going to accept a write. Maybe somebody can never read it again at some point in the future. Like, we don't know, possibly. Like, it would be cool if we actually know what kind of guarantees that we get out of our systems. So we need that. And the set of all of the things that could possibly happen is called a consistency model. So this describes in your system what you can and cannot do, what can and cannot happen. And these have been theoretically studied quite a bit. I don't think it's legible. That was not the point of the slide. I am not going to talk about every single consistency model on here. That would be a gigantic waste of time. They are, however, ordered by, I mentioned earlier, you can either have basically availability or consistency. The stuff in red with the thick lines starting on top is stuff that if you have that kind of model, you cannot be available, right? So you can basically formally prove under some models, et cetera, extensive hand waving here, that if that is your guarantee, then you cannot be available. There will be times where your system does not work, and it will just tell you, like, I don't know what the answer is. Then there's the stuff in blue, the very thin lines at the bottom. So there's stuff in there like read committed, read uncommitted. Those of you who have spent too much time with SQL databases might recognize those words. So those are things that you can have while available. So you can be totally available, and then you can see some of those effects. The stuff in the middle, in yellow with the medium thick lines, is stuff kind of in the middle where you can have it while being available, but only if you guarantee that a node will hit the same that a process will hit the same node every time. So earlier I had an example of, okay, something weird happens here when you hit a different node in between two processes. If you can guarantee that that never happens, you always read from the same node, then you can have these slightly cooler consistency models in the middle. These are all fairly theoretical, but they generally map to real systems fairly readily. There's a couple of words on there, like, for example, serializability. And that's an important one, so I'm going to explain what it is. So serializability means that out of all of these concurrent operations that are going on, so there's like a lot of stuff, there's a lot of operations, writes, reads, whatever. Serializability says that the eventual results could have been produced by some sequential execution of all of those concurrent things. So if you imagine that instead of all of these concurrent things happening, there is some universe where all of them happened in some specific order, any order, and you would have gotten the same results. Now that sounds really weak because I haven't said which order. All I'm saying is there is some order out there that I could have done this in and I would have gotten the same result, right? But there's a lot of orderings of all of the events in the world. So that can be very weak. So if you start with a register that's 0 and I issue 3 operations that all succeed, I write 0, I write 1, and I write 2, then at the end of this, it could be 0, it could be 1, it could be 2. All of those are entirely correct because I could say, oh, well, look, I got the write that wrote 2, I got that one last. So that's the value that I remembered. Or I could have seen 1 last, or I could have seen 0 last. All of those are completely valid within serializability. So that sounds like a pretty useless thing. However, the reason that it still works is because those are not the kinds of operations that you typically do with a serializable register. So what you do is you do a thing called a compare and swap. Those of you who have ever taken, maybe some assembly classes, a lot of CPUs have atomic compare and swap operations. So what the operations that you issue are not set it to 2. It's set it to 2. By the way, I'm assuming that it's 1 right now, and don't set it to 2 if it's not 1. And then just wait, don't succeed. Only succeed if it's currently 1. I think it's currently 1, and then write 2. So when you do that, then this set of very, very similar operations, there's only one possible way that it could be executed. Because the second one is the only one that can be executed at the start because x is 0 to begin with. So then you write 1 to x, and then you can do the third one because x is 1 now, and then you store whatever's in x, you put it in y, and then finally you do the first one. So there's only one, despite the fact that this is still only serializable, there's only one possible sequence of events in the world where this is where this can be executed in a serializable system. So you know that all the way at the end, x is always 1, y is always 2. Another nice one is linearizability. I'm mentioning that mostly because I mentioned it earlier as what the C in the CAP theorem means. So this is CAP theorem's consistency. And what linearizability says is that all operations appear to occur instantly. So earlier when I said, like, information travels at C, the lines are skewed, yada, yada, yada. Yes, that's true. They will still be skewed. They will still take some time to arrive, et cetera, et cetera. But the system, through various other guarantees, which involves a lot of consensus, a lot of nodes talking to each other, et cetera, it appears that you're writing to a single register, right? So you never see this effect where, like, oh, you see a stale read or something like that. And then finally, strong serializability, which is the one all the way at the top, which is stronger than everything else and encompasses everything else, is both linearizability and serializability at the same time. Earlier, I mentioned very briefly that your computer is distributed. Even your smartphones, like most of you have smartphones with like dual or quad cores or whatever, those things are distributed systems, right? And you can see distributed systems effects. So you can even have these models in centralized systems that just have to deal with a lot of concurrency. For example, SQL databases, you can typically configure what kind of consistency levels you want. You can see things like read committed, read uncommitted. They will prevent certain things from happening or allow certain things from happening. And again, this is all about trade-offs, right? You're trading performance. So when you say your SQL database, I don't really care if I'm seeing data that's in the middle of a transaction or whatever. Like it's okay if it's old or if it's new and it hasn't been committed yet, et cetera. That means that your database can make optimizations that it otherwise would not be able to make. Conversely, if you're asking for a very, very strong consistency model, that necessarily implies that your database has to make all sorts of guarantees to make sure that you don't see inconsistent data. And that's expensive. That requires, in a distributed system, that requires talking to all sorts of nodes, making sure that what they have, so that if you accidentally go to that node, that you don't see a wrong value. So Python doesn't really have a lot of strong concurrency tools there. But another programming language that I really like, called Clojure, is pretty much banked on concurrency, and they have multiple kinds of references. So like when you do in Python you can say like X is some object. So in Python we really only have one kind of reference, a couple if you include like recurves and stuff. But in Clojure you can have multiple kinds of references that only differ in what kind of consistency models that they allow. So for example, in Clojure you can have software transactional memory. So you can run transactions exactly like you would in a SQL database, except instead of running them in the database and you have to write some SQL, and you're limited by what your database allows within that transaction. For Clojure, you can write arbitrary code and execute that over a reference. So when doing, this is a fairly advanced talk, so if this doesn't make sense and your eyes glaze over, don't be afraid. So while doing this, I tried to figure out what the difference was between, or what the concurrency models were in Python. Now, I'm a Twisted Core contributor. I'm a big fan of Twisted, love Twisted. So a very common alternative to Twisted is multi-threaded programming with a bunch of blocking I/O. Now, I tried to figure out what the consistency model within Twisted was. And I'm reasonably sure that it's strongly serializable. The reason is Twisted is an event loop. It has a single thread. This also goes for like async I/O and a bunch of other ones, but I just looked at it for Twisted. So there's an event loop with one reactor thread. I noted it's serializable because serializable means there is some sequence of events in which I could execute all of this stuff sequentially, and I would have gotten the same result. Well, Twisted does execute code sequentially. It just does I/O in parallel, but that's OK. It runs code sequentially, so I know it's serializable because that's what the reactor does. It finds the serialization that works. And then it's also linearizable because the callbacks run by themselves. So from the point of view when I'm in a callback, it looks like I'm the only thing that's going on. And also when I'm in a callback, I don't see any other callbacks doing stuff at the same time. So then I wondered, OK, what is Python's consistency model? If I write some Python, what do I get? And the answer is literally nobody knows. So some people tried to figure this out for unladen swallow. They tried to get rid of the GIL. So they spent a lot of time trying to figure this out. And basically, there's a PEP written. I don't think it's actually an official PEP. I think it might just be a draft. But they talked about a number of consistency models. And the problem was that CPython never really defined what it was. CPython just accidentally had one by virtue of being a program that you can run. And it was very hard to figure out, like, OK, what are the guarantees that I happen to have because I'm running on CPython? What are the guarantees that Python gives me by default, right? So it turns out that it is basically whatever your CPU guarantees, which is not really a lot these days, except it's probably fine because there's a GIL and all your objects live on the heap anyway. So maybe, I don't know. Plus, like all multi-threaded code has totally correct use of mutual exclusion systems like semaphores and locks, right? Yeah, it's fine. Cool. So let's talk about time. We want time in distributed systems, right? Time passes. Progress is made. So one idea of time is a global clock model, where you have a bunch of nodes. They're all interconnected. You might not be able to see the lines. You're going to have to trust me. And they're all talking to the same clock. So the thing in blue is the thing with the clock. Now, that global clock model means that everybody has the same clock, and all accesses to that clock, they're instant. The uncertainty is 0. Everybody sees exactly the same clock. It has a really cool effect. It means that if I see a timestamp from somewhere else, I can compare them, right? Because this is like, you have one timestamp that says that something happened on Saturday, and another that says that it happened on the day after, or it says Sunday, and then I can compare them. I can say, like, OK, cool. So it was exactly 23 hours and 18 minutes and 15 seconds in between these events. So the mental model of this, you can think of it like an office. There's a wall clock on the wall. Everybody sees the wall clock. Everybody knows exactly what time it is. Or, James Bond movie, everybody synchronizes their clocks before he gets started. Another model is the local clock model, where no global clock, but all of the individual nodes have their own clock. And each one of those clocks is reasonably reliable. The problem with this is that they will start to diverge, right? Because they're not exactly the same clock. And so you can't really compare other timestamps. I mean, you can get an approximate idea, but there's going to be some issues there. The mental model for this is a stopwatch. So you have a team, everybody gets a stopwatch. You know when 10 seconds have passed, but that doesn't mean that you can know when, did something else happen 10 seconds ago on this other node over there. And then finally, which is mostly a theoretical model, there's the no clock model. Literally, nobody knows what time it is. We don't know how much time has passed. We don't know what time it is. We know nothing. Turns out, theory ruins the day again. Science ruining everything since 17-something. That you can't have a global clock. You can pretend that they almost exist, but you're going to be wrong pretty often. To illustrate that, Google has a thing called Spanner. It's a distributed database. And so they use GPS and atomic clocks. If you didn't know how GPS works, hint, it's really precise clocks. So what they do is they have a lot of GPS receivers, like a lot of GPS receivers, and they have atomic clocks, like literally rubidium fountain clocks. Somebody moved those into a data center, right? And in their paper, they actually say, the atomic clocks drift significantly. When you think that atomic clocks have significant drift, you probably have a problem. And then finally, their results are like the uncertainty is generally below 10 milliseconds. OK. So that sounds really good. 10 milliseconds is not a very long time until you realize that there's 100 of those every second. Now, 100 requests a second is not that much. I'm not saying that all of those requests are maybe banging on the same thing, but like this is not perfect. It's really, really good. And I'm not trying to hate on Google Spanner or anything. Like they did a thing and they needed to do that thing. Like there was a perfectly valid reason for doing it. My point is you can't even get global clocks even if you have millions and millions and millions of dollars to spend and somebody who's going to OK an expense report for like $10 million worth of atomic clocks. So on the other hand, you also can't have no clocks. There is you basically need them for failure detection. The way that failure detection typically works is you wait a while, and if you don't hear anything for, let's say, a second, 10 seconds or something, then you assume like, OK, look, either the network is hosed or the host is down. I don't know what's going on, but I'm definitely not going to hear an answer back. So by waiting a while, you can differentiate between, is this just the network being a little slow or a host being a little slow versus is it actually broken and it's not going to fix itself? Obviously, that's a heuristic. It doesn't work all of the time. You can't make it work all of the time. There's an interesting theoretical result called the FLP result that basically says, I'm not going to go into too much detail, but essentially you can't have a distributed system then because like you can't get machines to agree on any value ever, and that's very problematic. Timestamps, however, are often a proxy. You don't actually really care what the timestamp is. I mean, maybe you do for displaying it to a human, but then the uncertainty on that is typically acceptable. Like you don't need to know the exact microsecond at which a transaction got committed to a database. You probably want to know if it was 5 p.m. on a Friday or something. So timestamps very often don't really have to match real-world time. If you have a timeline, let's say that this is a number of things happening to a single register. So I'm writing X, writing Y, et cetera, et cetera. Now I've marked these as T0, T1, T2, T3. Those could be real timestamps. It's also possible that they're just integers, right? Very often my application doesn't really care that this was the thing that was written on Saturday at that time. My application cares that this was version 2. and it's read version 2, and now it's writing version 3, right? So it cares about version numbers. So very often you can get away with that. Not the first person to have that idea. These are typically called Lamport and vector clocks. So informally, again, I don't really have a lot of time to go into extensive detail on everything. So Lamport clocks means that you keep a version number of what you've seen, right? So you have the data, and then you know, like, this is the 7th version of this data. And then a little bit more complex, vector clocks means that you keep version numbers of everything that you have seen that other nodes have seen. So basically, whenever you communicate something, you pass along that entire big vector of versions that you know other nodes have seen. The reason you want this is if you have a lot of writes going together, then at least you can detect when there's conflicts. So a lot of systems like, for example, REAC, which is a distributed database, it's really good, you should use it. Use vector clocks to figure out when stuff has gone wrong. I do have some good news today. So most of that was kind of bad. Like, a lot of it was theory. It was like, you know, the CAP theorem, you can't have nice things. The FLP theorem, you definitely can't have nice things. You know, it's a pretty bad scene. But that said, we're here at PyCon, and we have a lot of employers that run really, really big systems. And so clearly it's not as bad as I just said, because obviously some people do actually manage to produce working distributed systems. I mentioned Google earlier. Google has a massive, like, uncountable number of nodes, and they're all talking to each other, and they seem to be producing these systems like Chubby and Spanner, and they put out white papers. And when I go to Google, it usually works. So obviously, some of this stuff is actually right. So there is stuff that you can rely on. And one very simple thing that a lot of systems end up implementing is queues. I'm not really going to talk about queues because basically there's a really good queue talk every year at PyCon, and they're all recorded, so go to YouTube, watch one. I mean, basically the idea is that you have too much work to do on some front-end node, so you just shove it in a queue, and it's somebody else's problem, and eventually somebody will take care of it. It's a very simple paradigm. It has very reliable software, and it solves a heck of a lot of problems. For slightly more complex things, you need consensus protocols, for example. Now, I talked earlier, you might remember the example where I talked about Quorum as a way of maintaining consensus in a cluster, and then I showed with the one where A could talk to both groups, like, hey, it doesn't actually work that way. So consensus protocols are things that do actually work that way. Consensus protocols are a way to get a number of machines to agree on a value. Turns out that it is about as hard as getting humans to agree on a value. So real tricky. There's a couple of big ones. One algorithm is called ZAB. It's commonly used by Zookeeper. Zookeeper is basically the thing that you should use. Unfortunately, it's on the JVM, so for a lot of us, it has some operational issues in the sense that now you have to learn how to operate the JVM. But the alternative is significantly worse, so just use Zookeeper. Then there's also Paxos. For example, Google's Chubby distributed log service uses Paxos. I put Paxos there with a star. Paxos is notoriously difficult to implement. Actually, my job interview ended up basically me ranting about 4 hours about Paxos. Like, the problem is one of my interviewers who also knew Paxos, like, we couldn't even really agree how many phases there are in Paxos. Like, there's a 2-phase camp and the 4-phase camp, and, like, who knows? It's really tricky. The other thing is, like, when you look at the papers, very often people don't end up implementing Paxos. They end up implementing Paxos with an asterisk with some stuff, like, actually that not even in the Paxos paper, because it turns out that otherwise you can't really make it work. Finally, there's a new contender. There's Raft. I gave the example of etcd. So Raft is really interesting because it was specifically designed as a design constraint. Let's make this easy to understand. And they actually have some science to back this up. They taught both Raft and Paxos to a bunch of students, and overwhelmingly the students understood Raft and did not understand Paxos. That was actually really good. It's a wonderful paper. If you are really interested in this stuff, you should go read it. Now, getting stuff to agree on a value, getting computers to agree on a value is not terribly useful all by itself. You probably want something more than that, right? You don't want your computers to just agree on something. You want something a little bit more useful and closer to your application domain. So Zookeeper calls this recipes. I've copied the term. You can do this equally well in Zookeeper as you can anywhere else. So these are things that operate on top of consensus protocols. And you can get things like locks. So you can actually, in a distributed system, you can have a lock. You can make sure that I am the only person doing this thing right now. Right? It can be very useful. Sometimes your application has to do something that is a side effect, right? Maybe you're like, I don't know, making some phone calls or sending some letters or even sending some email. Like you want to make sure that you don't have a race condition where if you have two of the same requests coming at the same time that you accidentally send 2 phone calls or 2 emails or 2 whatever. You want to make sure that there's only one thing at a time doing that. And you can do that fairly easily with consensus protocols. Another thing is barriers. It's kind of like the inverse of a lock, in the sense that in a lock you're making sure that you're the only thing doing something. With the barrier, you're waiting until everything reaches a certain point, and then you can continue. So that's like if you want to make sure that like you don't end up incurring a backlog or stuff like that, then you can use barriers. And another really cool one, and I'm going to go into that a little bit more because we use it at work, is set partitioning. So basically it just means I have a set. I would like them to be partitioned across many of my nodes. So for example, you can have the numbers 1 through 5, and you just plug it into some software, and each of the nodes will think that they own this particular one particular value in this case. And when that fails, this is where it gets interesting. When that fails, the consensus algorithm recognizes that it fails and redistributes. So you can suddenly this one node has 2 elements to handle. So that's really interesting if you want to. So for example, we use it for, we get issued a lot of requests over our HTTP API, and we do stuff somewhere. In our case, we create servers. Obviously, you don't want to create too many servers because then users get overbilled. You don't want to create too few servers because then users' websites go down. Either way, users are going to be unhappy. So what we do is we use subpartitioning to figure out, given a particular request ID, some ID that you get from the request, who does this belong to, right? There's always going to be, and in that sense it's very similar to a lock, there's always going to be one node that is, and exactly one node, that is responsible for doing that particular piece of work. And that way we can guarantee that you don't accidentally, for example, if a customer says, hey, can you get rid of 2 of my servers? That we don't have 2 nodes that go like, yeah, sure, I can get rid of 2 of your servers and end up killing 4. Or stuff like that. Final thing I'm going to talk about, something I'm really excited about, CRDTs. This is like my favorite. I love these things. So they're conflict-free replicated data types. So the problem is, so far, every time I've been talking about operations, you read something, you perform some computation, like you increment a number or whatever, and then you write it back. When you have multiple concurrent operations, that means that once in a while you're going to get a conflict, right? If I have 2 operations that read at the same time and they do something and they write back, and suddenly I have these 2 values and they're not necessarily the same, what do? One solution is to throw one of them away. It doesn't really work too well. It's typically called last write wins, or most writes lose. And the other alternative is coordination, right? You can make sure that everybody basically goes around the cluster and says like, yes, I own this value now. Do I own this value now? You do 2-phase commits, so you do a lot of back and forth. It's like TCP but worse. But that's really expensive, right? And this is what we talked about earlier. You have the trade-off between availability and consistency. And when you pick consistency, you're going to get rid of availability. You're going to get rid of performance. So I want highly available data stores, but I don't want nonsense data in my database. Seems like a reasonable thing to want. Turns out that this is something that research has only really fixed in like the last 5 years or so. So one of the ideas is that you describe what you want and you describe how to resolve eventual conflicts. So instead of what I did before, which is I read a thing and then I do something to the thing and then I write the result back, you're going to say, please go ahead and do this to the thing. And then you can do a lot more interesting things. So CRDTs are typically specialized. There are two ones that I'm going to talk about. They're, as far as I know, the only 2 ones that have been defined. They can be commutative or convergent. With commutative RDTs, what you're going to do is you're going to broadcast the actual operations. And then you have a merge operation that can merge multiple of those operations into one data point. So this is going to be commutative, so I can flip the order. It's going to be associative, so it doesn't matter what order I do stuff in, but it's not necessarily idempotent. If I apply an operation multiple times, I'm going to get a different result back, or I might get a different result back. So a simple example of this is integers. Let's say that you're adding numbers, subtracting numbers, and if I have the list +1, -2, +3, +5, -4, no matter what order that I add those together, I'm always going to end up with 3. However, if I see any of the operations more than once or not at all, then I'm going to get the wrong answer. So that's an example of a simple CRDT. Alternatively, convergent RDTs are going to broadcast states. And some of those states can be partial, like I don't know what the final result is. Nobody knows what the final result is. But I'm going to tell you what I have right now. And then when you get that value that I just sent you, you're going to merge it with whatever it is that you know. And eventually, if we just put all of our minds together, we have all of the information that we need. So this operation, it's commutative, associative, idempotent. Informally, it just means like you can apply it lots of times, and eventually you'll always get to the same result. And it doesn't matter what order you do stuff in or anything like that. So for example, if I have a set on top with the number 1 in it. I have one writer that adds the number 2. I have another writer that adds the number 3. And there's only one way that I can merge those two sets, and then eventually I end up with 1, 2, 3. If I hadn't had a CRDT, and I was just doing last write wins, one of these two writes would have been lost. You can do more complex stuff. So this is, here I'm writing all of the, on the left side, I'm writing the numbers 1, 2, 3, 4 separately, and they get merged neatly like that. On the right side, there's a node that had some, I don't know, some network issues or something, and it's 1, 2 from some node, 1, 2, 3 from somewhere else, and it got the writes 3 and 4. But you'll notice that if you just merge them, if you just keep merging, keep applying the merge operation, if you do eventually see all of the writes, then eventually you will always end up with the same set. Now in practice, it's virtually always a convergent RDT, so the kind that submits states. I'm not sure why that is. I have a theory. The theory is that if you, the hard problem with the convergent bit is writing the actual algorithm that does all of this, right? You have to write the merge function. You have to figure out what your internal data structure is. That means you have to solve a local problem once. Maybe it's a hard problem, but you just have to solve that one local problem. With the commutative thing, you have to make sure that all operations are delivered exactly once. That means you have to solve a really, really hard distributed systems problem all of the time. So as basically the crux of this talk, distributed systems trickier than you might think. In practice, it ends up being convergent RDTs because you can actually use them. Because you don't have to solve that hard distributed systems problem of making sure that each operation arrives once. There's a lot of examples of these. I'm not going to go through all of them, but there's like counters, so you can count up and down, and these will be consistent. You can have sets. There's a couple of different examples of sets. You can have maps. Really, those are just implemented as sets, so that's kind of cheating. You can have graphs, also just implemented as sets, kind of cheating. You can have registers. That's like the super simple example of what I was talking about. You'll notice that last write wins is technically a CRDT in this, but like it's not a very useful one, obviously, because occasionally you will throw some data away. And then finally, there's sequences, which is really cool. So sequences is stuff like a list. So these were developed mostly for operational transforms, which is the cool bit of technology that makes it so that when you write stuff in Etherpad or Google Docs at the same time with multiple writers, that actually works. So they will basically try to store stuff in the middle of a sequence. That is probably the one that's the most complicated. If you're interested in this, there's a seminal paper on basically all of these. Most of these are fairly simple to understand. The sequences one is a little tricky. It comes at the end of the paper for a good reason. Finally, using CRDTs, like designing them is tricky most of the time. Using them, however, is fairly easy. I already plugged Riak. I'm going to plug Riak again. I believe I tweeted a while ago, it's very hard to do an introductory distributed systems talk without repeatedly plugging Riak, because Riak is awesome. Riak has all of the, or has flags, registers, counters, sets, maps, etc. And they're fairly easy to use. So, to wrap up. Yay, distributed systems. They're more resilient. They are more performant. At least they can be more resilient. They can be more performant. And more importantly, they make some problems tractable. Clearly, no amount of really fast computer is going to make Google something that you can do on a single machine, or Facebook, or any other large distributed system, right? So there's stuff that we can do that we can't do any other way. But, distributed systems. They can be very hard to reason about. There's a huge state space, right? The amount of possible orderings of all of the events in the world is pretty much infinite. Like, there are no repeat scenarios. It's very, very hard to debug. They can also be expensive to operate, right? Definitionally, 5 machines are at least 5 times as expensive as 1 machine. But lots of distributed systems. Everything is about trade-offs. You have to figure out what's right for your application. Don't build what's off the shelf. Stuff like Zookeeper, you're not going to get it right if you try it yourself. So use the tools that are available. So why distributed systems? Because you're out of options, pretty much. And a lot of us are. Like, don't take that as advice. Don't do distributed systems. And that's all I got. Thank you. "44 minutes and 57 seconds in a 45-minute time slot, by the way."
I'm afraid we have no time for questions.
Yeah.
If you
Unless
haven't
you can
noticed.
fit in like those 3 microseconds.
Thank you all.
I will be taking questions like outside. Just grab me. We do need to vacate the area for the next speaker, though.